Join us for an in-depth exploration of James Clerk Maxwell's revolutionary discovery of molecular speed distributions in gases. In the mid-19th century, scientists were puzzled by the behavior of gas molecules. How fast do they move? Do they all move at the same speed? Let's begin by understanding the scientific landscape that Maxwell entered. Before Maxwell's work, scientists made the simplifying assumption that all molecules in a gas moved at roughly the same uniform speed. This early model showed all molecules moving at identical speeds, like soldiers marching in formation. But this didn't match experimental observations. The problem was that experimental measurements consistently showed that molecules had widely varying speeds, not a single uniform value. In 1860, the brilliant Scottish physicist James Clerk Maxwell decided to tackle this discrepancy using mathematical reasoning and physical insight. Maxwell began with two fundamental assumptions about molecular motion. His first assumption was that the x, y, and z components of velocity are statistically independent of each other. Mathematically, this means the joint probability equals the product of individual probabilities. The x velocity doesn't affect the y velocity. His second assumption was that space is isotropic, meaning there's no preferred direction in the gas. The distribution should look the same in all directions. This symmetry means molecules are equally likely to move in any direction. There's no up, down, left, or right preference in the gas. Now let's see how Maxwell used these assumptions to derive his famous distribution. You might ask, how do we mathematically express the idea that the distribution depends only on speed, not direction? The answer is that the probability must depend only on the square of the speed, which is v-x squared plus v-y squared plus vz squared. When we combine the independence assumption with isotropy, we get a powerful mathematical constraint. A product of functions equals a function of the sum of squares. This is only possible with exponential functions. Maxwell showed that the only mathematical function satisfying both conditions is the Gaussian or normal distribution. For each velocity component, the probability is a times the exponential of negative mv-x squared over 2 k-bt, where m is molecular mass, kb is Boltzmann's constant, and T is temperature. But scientists don't measure individual velocity components. They measure molecular speeds. How do we get from components to speed? The speed is simply the magnitude of the velocity vector, calculated as the square root of the sum of squared components. This is just the Pythagorean theorem extended to 3 dimensions. To find the speed distribution, we transform from Cartesian velocity coordinates to spherical coordinates, where speed is the radial variable. The crucial insight is that in spherical coordinates, the volume element includes a factor of v squared, representing the growing surface area of velocity space spheres. This gives us the Maxwell speed distribution, 4 pi, versus squared times a normalization constant, times the exponential of negative m, versus squared over 2k-bt. Let's visualize and understand the shape of this remarkable distribution. Here's what the Maxwell distribution looks like. Notice it starts at 0, rises to a peak, then falls off exponentially. This is the famous bell-shaped curve, but skewed to the right. The distribution starts at 0 speed, because the versus squared factor in the equation forces the probability to 0 as speed approaches 0. It then rises to a maximum at what we call the most probable speed, where the largest fraction of molecules are found. Finally, it has a long tail extending to high speeds due to the exponential decay term, representing the small but non-zero fraction of very fast molecules. There are 3 important characteristic speeds in the Maxwell distribution, each with different physical meanings. The most probable speed is where the distribution reaches its maximum. This is the single speed value where you'll find the most molecules. The most probable speed equals the square root of 2k-bt over m. It depends on temperature and molecular mass. The mean, or average speed, is the weighted average of all speeds across the distribution. The mean speed equals the square root of 8 k-bt over pi m. Notice it's slightly larger than the most probable speed due to the distribution's asymmetry. The root mean square speed is the square root of the average of the squared speeds. It's directly related to the average kinetic energy. The RMS speed equals the square root of 3 kbt over m, This is the largest of the three characteristic speeds. Here are the three characteristic speeds marked on the distribution. Most probable is leftmost, mean is in the middle, and RMS is rightmost. Let's calculate actual numbers for oxygen molecules at room temperature to make this concrete. Consider oxygen gas, O2, at room temperature, which is about 300 Kelvin or 27 degrees Celsius. The mass of an O2 molecule is 32 atomic mass units, which equals 5.3 times 10 to the negative 26 kilograms. Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin. Temperature is 300 Kelvin. Let's calculate the most probable speed using our formula. VMP equals the square root of 2 times 1.38 times 10 to the negative 23 times 300 divided by 5.3 times 10 to the negative 26. This gives us approximately 395 meters per second. That's faster than the speed of sound in air. Now let's calculate the mean speed. The mean speed is approximately 445 meters per second, which is about 1,000 miles per hour. And finally, the root mean square speed. The RMS speed is approximately 483 meters per second. These are incredibly high speeds. You might wonder, if molecules move so fast, why don't we feel constant wind? The answer is that they move randomly in all directions, so the net momentum transfer averages to zero. How does the distribution change with temperature? This is crucial for understanding gas behavior. Here are three distributions at increasing temperatures, T1, T2, and T3. Notice how the peak shifts right and flattens as temperature increases. At higher temperatures, the entire distribution shifts toward higher speeds because molecules have more thermal energy. The distribution also becomes broader and flatter, meaning there's a wider range of molecular speeds present in the gas. The most probable speed is proportional to the square root of temperature. Double the temperature, and speeds increase by a factor of square root of 2. Different molecules have dramatically different speed distributions due to their mass differences. Consider hydrogen gas with molecular mass 2 compared to nitrogen with molecular mass 28, both at the same temperature. The most probable speed is inversely proportional to the square root of mass. Lighter molecules move faster. For hydrogen at 300 Kelvin, the most probable speed is approximately 1570 meters per second. For nitrogen at the same temperature, the most probable speed is only about 420 meters per second. Here we see hydrogen molecules have a much broader, flatter distribution extending to higher speeds, while nitrogen has a narrower, taller peak at lower speeds. This mass dependence explains why light gases like hydrogen and helium escape Earth's atmosphere over time, while heavier gases like nitrogen and oxygen remain trapped. How did scientists verify Maxwell's theoretical prediction? This is where theory meets experiment. Early experiments used molecular beam techniques, where gas molecules stream through a small hole and their speeds are measured. A molecular beam apparatus has a source chamber with a small hole, allowing molecules to escape. Different speeds arrive at the detector at different times or angles. Otto Stern's famous molecular beam experiments in the 1920s provided direct confirmation of the Maxwell distribution. Modern techniques like laser spectroscopy and time-of-flight measurements can measure velocity distributions with incredible precision. When experimental histograms of molecular speeds are plotted, they match Maxwell's theoretical curve with stunning accuracy. The bars represent measured data, the curve is Maxwell's prediction. The agreement between theory and experiment is excellent across different molecular species, temperatures, and experimental conditions. Maxwell's distribution is intimately connected to the broader kinetic theory of gases. Kinetic theory connects the microscopic motion of individual molecules to macroscopic properties like pressure and temperature that we can measure. A key result is that the average kinetic energy equals 3/2 kBt. This directly relates molecular motion to temperature. Gas pressure equals 1/3 times the number density times mass times mean square speed. Faster molecules create higher pressure through more forceful collisions. Why the factor of 3? Because in 3 dimensions, molecular energy is equally distributed among x, y, and z directions, and pressure comes from only the component perpendicular to the wall. In a gas container, molecules move randomly in all directions. The pressure we measure is the cumulative effect of countless molecular collisions with the walls. The Maxwell distribution is a specific example of a more general principle called the equipartition theorem. The equipartition theorem states that in thermal equilibrium, energy distributes equally among all available degrees of freedom. Each quadratic degree of freedom gets an average energy of 1/2 kBt. For translational motion, there are 3 degrees of freedom corresponding to motion in x, y, and z directions. Therefore, the total translational energy is 3/2 kBt. Real molecules also have rotational and vibrational degrees of freedom, each contributing additional energy according to equipartition. The distribution is often called the Maxwell-Boltzmann distribution. Let's understand Boltzmann's contribution. Ludwig Boltzmann generalized Maxwell's distribution to include not just kinetic energy, but also potential energy in external fields. The probability is proportional to the exponential of negative total energy over kBt, where total energy includes both kinetic and potential contributions. A classic example is how atmospheric pressure decreases with altitude. Molecules at higher altitudes have more gravitational potential energy. Pressure at height z equals ground pressure times the exponential of negative mgz over kBt. This is the barometric formula. This explains why the air is thinner on mountaintops. Fewer molecules have enough energy to reach high altitudes against gravity. Maxwell's distribution has applications far beyond 19th century gas theory. In plasma physics, ions and electrons often follow Maxwell distributions at different temperatures, crucial for understanding fusion reactors. In astrophysics, Maxwell distributions describe stellar atmospheres and the motion of gas in interstellar space. In chemistry, reaction rates depend critically on the high-energy tail of the Maxwell distribution, since only fast molecules have enough energy to react. The Arrhenius equation for reaction rates has this same exponential form, showing K equals A times the exponential of negative activation energy over kBt. In semiconductor physics, electron and hole velocity distributions follow Maxwell-Boltzmann statistics modified by quantum effects. While Maxwell's distribution is remarkably accurate, there are situations where it breaks down. At very low temperatures or high densities, quantum effects become important, and the Maxwell distribution must be replaced by quantum statistics. Particles with half-integer spin, called fermions, follow Fermi-Dirac statistics due to the Pauli exclusion principle. Particles with integer spin, called bosons, follow Bose-Einstein statistics, which allows phenomena like Bose-Einstein condensation. The Maxwell distribution only applies to systems in thermal equilibrium. Far from equilibrium, velocity distributions can be quite different. In laser cooling of atoms, for example, the velocity distribution becomes much narrower than a Maxwell distribution, enabling temperatures near absolute zero. At very high temperatures, where molecular speeds approach the speed of light, relativistic corrections modify the distribution. Maxwell's work had profound impact on physics and our understanding of nature. This was one of the first successful applications of probability and statistics to fundamental physics, showing that deterministic laws could emerge from statistical behavior. It provided the crucial bridge between Newtonian mechanics of particles and thermodynamics of bulk matter. Maxwell's work directly influenced the development of statistical mechanics by Boltzmann, Gibbs, and others. Maxwell's groundbreaking work in 1860 laid the foundation for modern physics. In conclusion, Maxwell's distribution is a fundamental concept in physics with far-reaching implications.